Okay, so I think we're ready to start. Thank you for joining. So it's a great pleasure today to be participating in the ARC-AGI tour, and we're welcoming Mike Knoop and François Chollet. So I'll just say a few things. I'll introduce them. First of all, some logistics. We are recording the event. So because of that, please hold your questions until the end. And at the end, if you have questions, obviously, feel free to ask the questions, but please use the mic so that we can get the questions and also the answers. And the event after recording will be available through the Hariri Institute YouTube channel. So just a few words to introduce Mike and François. Mike Knoop, he's the co-founder of Zapier, and he's the ARC Prize co-host. He has led at Zapier all product development and engineering before shifting his focus to AI R&D in the summer of 2022. At Zapier, he launched Zaps, Transfer, Tables and Interfaces, AI Actions, and Central AI Bots, as well as leading Zapier's OpenAI partnership. He has partnered with notable AI researcher François Chollet to launch the ARC Prize, which is a 1 million plus competition to restart an open source artificial general intelligence progress. Mike is a builder with a background in engineering, math, research, and programming, and he's very passionate, as I'm sure you will experience, about frontier and open source AGI research. François Chollet, who is the founder of Keras, and he's the ARC Prize co-host, is an engineer and researcher in artificial intelligence. He's the founder of Keras. He has received his diplôme d'ingénieur from l'École nationale supérieure de technique avancée in Paris. Has been awarded the Global Swiss AI Award for breakthroughs in artificial intelligence. He's the author of Deep Learning with Python and the creator of the Keras library that I'm sure many of you know and use, which is a deep learning library in Python used throughout industry and academia, I would add. In 2019, he introduced the ARC-AGI benchmark in a very celebrated paper on the measure of intelligence. And in 2024, he co-founded the ARC Prize together with Mike. So we'll hear them introduce and present this prize. Thank you so much. Thanks for joining us.
All right. All right, I'm going to be speaking first and then Chollet. One run of show thing as well. So we put this QR code up here. This is for Q&A. So we're trying a new thing, Dory. You can basically, throughout the talk today, submit your questions. You can upvote other folks' questions as well, and we'll use that if there's a lot of questions at the end to figure out kind of how to prioritize. We're also going to be hanging out afterwards too, so hopefully that's a good way. And we'll show the QR code again, and I think there might even be some links maybe on slides. Yeah, down in the bottom that you can get to as well. Okay, so I actually want to start by talking about something you might not have expected us to talk about, given that we are here to talk about ARC Prize, which is I want to tell you the story that I think we like to tell about as a field, the history of artificial intelligence. Since basically the beginning of the field, research has sought to build AI systems by leveraging human knowledge, right? Human insight, understanding into the nature of intelligence, the nature of the brain, neuroscience. And while this has been somewhat the favored method, I think, amongst researchers, it was also just the pragmatic view, right? We didn't have cheap compute. It just didn't exist at that point. The cost of compute has been falling consistently. It's basically 2 orders of magnitude for every decade, going all the way back to 1940. So we're in our like 8th or 9th decade now of this progress. And finally, in the 2010s, and this was enabled by the cheap abundance of GPUs, these deep learning methods finally started to work, right? From image recognition, from ImageNet to the transformer, we started to see these general purpose search and learning algorithms get applied to ever more impressive AI domains. Things that were sort of previously thought impossible, right? Things like image recognition or self-driving cars or very complex games like Go or protein folding and even language. This price performance curve, by the way, continues all the way through today, probably at least the next 10 years. I don't think there's any sort of suggestion that it's going to slow down soon. And you can do cool things with this, right? You can like predict the cost of what it took to train GPT-4. If you were trying to train GPT-4 in a month, for example, it last year probably would have been about $400–500 million, which is about accurate by the speculation. And 10 years ago, that would have been $40 billion. So kind of in the realm of nation-state projects. And 10 years from now, only $4 million, in the realm of like what you could go raise for like a seed fund at a startup, right? So really interesting to see, I think, the implication of this. Now, language modeling, I think that last example I shared turned out to be even more powerful than most folks expected. These language models started sort of reaching human capacity on all of these AI reasoning benchmarks that we could create and throw at them. That's what this chart is showing. And more so, not only are they reaching human capability, but they're doing it faster, right? This x-axis here is indexed from since the benchmark introduction. And so they're sort of scaling up to meet these human capabilities faster and faster. And I think this shows that these general purpose search and learning methods empirically work for a lot of these benchmarks. And most of the industry believes that this progress is going to continue, this acceleration is going to continue, scaling up all the way until we get to artificial general intelligence. I think we like to tell this story as an industry because it fits the data we have, right? Over the last 10, 15 years of scaling progress in deep learning, as well as the last 80+ years of scaling progress in the price performance of compute. But I think the conclusion that deep learning can scale all the way up to artificial general intelligence, it assumes a very specific definition of AGI, and that is one that is oriented around the AI's ability to demonstrate skill, as opposed to an AI system's ability to actually learn skill in the first place. That's why in 2019, as Giannis mentioned, Chollet published the ARC-AGI benchmark to test, can AI systems efficiently learn skill and apply it on open-ended problems or not? 5 years later, as we sit here today and talk to you all, it is still unbeaten. In fact, heading into June this year, when we first launched it, progress, you can kind of see the yellow curve here, it had even been like decelerating over time. So what if scale is not all we need to reach AGI? No matter which side of the scaling hypothesis you're on, I'm sure some of you agree with it, some of you disagree. No matter what you think today coming into this, for the next half hour, I invite you to sort of put on your curiosity hat as we explore the answer and implication of that question. So if you've never seen ARC, you might be curious, first of all, what is this benchmark? What does it look like? Shows better than tell, so here's an example of an ARC test. There's hundreds of these across the data set, and your job is to find the pattern from the example in to the example out, and then apply that pattern on the test here. So in this case, if we look at the left end example here, looks like we're trying to figure out like which of those red blobs do we turn blue. And probably by doing it, we're drawing these straight lines connecting the sort of blue dots on the margins, and anywhere it intersects with one of those red blobs, we're gonna turn it blue. We picked this example, by the way, because this is, I think, a good one that shows how straightforward and easy ARC tasks are for humans. And yet, this is an example from our data set that we know AI cannot solve today. I mentioned this data set has hundreds of these puzzles. Every single one of them is unique from the training data. And I said they're designed to be very straightforward for humans, but very hard for AI to solve today. We even have some human testing data that suggests somewhere around 98–99% of smart humans can solve all of the, or one human can solve, I should say, 98 or 99% of all the ARC puzzles. When I rediscovered the ARC benchmark a couple years ago, I was pretty surprised that it hadn't been saturating up like all those other AI benchmarks. And my own curiosity got sparked. I wanted to know what makes this particular benchmark so special and so resilient to being beaten by all of our modern AI systems today. I think there's a handful of things. The first is this idea of task novelty. Every single task is novel and unique from any potential training data, and so that means there's no easy or straightforward way to cram for ARC. And this is in contrast to how deep learning works, right, at a fundamental level by improving accuracy on your task by adding more and more example into your sort of pre-training data. Effectively, you're memorizing answers, you're memorizing situations with these deep learning approaches. I think the other unique and novel thing that makes ARC special is that it only assumes a handful of core knowledge priors in order to solve these puzzles. These are core knowledge priors like basic counting, basic topology, basic geometry, symmetry, reflection. These are core knowledge priors that you acquire as a child really early on in child development, probably before you even reach 5 years of age. not only does ARC require to express those core knowledge priors, you have to be able to abstract and compose on the fly using those core knowledge priors. The state of the art that we should report on that benchmark, and you'll see a few times today, is also reported on a private set. So there's a public set of tasks that you can go find in GitHub, but there's a private set of 100 puzzles that very few humans have ever seen. And that's what we actually use to measure the state of the art. And so this helps a couple things, but one of the main things is it helps us increase the confidence when someone actually shows up with a state of the art result, that we can increase our confidence this is actually a true progress mark, right? It decreases the likelihood that they were able to overfit or contaminate on the data set because they've never seen it before. And then I think the last thing that ARC does is pretty special is it requires efficiency. You get 2 guesses per task, and on the official Kaggle competition, you get a limited amount of compute to solve all 100 tasks. This is in contrast to maybe more brute force methods, right? Which I think is good demonstration of skill when you can brute force, your way through a search or finding an answer. But I don't think brute force is a good demonstration of intelligence, as we'll get into today. Unfortunately, ARC's been relatively obscure. When I started asking people, or at least in the Bay Area, hey, have you heard of this thing in the AI industry? Probably like less than 10% of the researchers that I had met had ever even heard of like what this benchmark was. And yet, 5 years in, right, ARC's durability suggests that we need some new conceptual breakthrough and progress to discover AGI. And if that's true, it means ARC might be the most important benchmark that exists in the entire world right now. Way more people should know that this thing exists. And so that's why Chollet and I decided to team up to launch ARC Prize this summer. It's this $1 million nonprofit competition to beat ARC, beat the benchmark, and importantly also open source the solution. It's a bit of a grand experiment, I think we'd say, to sort of test this hypothesis on the largest scale possible. Can frontier AI techniques and approaches beat ARC today? Now we're 3 months in, adding that little tip up. I'm proud that there's some progress, but I think we can more confidently answer this question: can frontier AI ideas beat ARC? And the answer is no. We're not there yet. This large prize of $1 million helps clear. It's kind of like a clearinghouse, right? It helps clear the space of all the sort of low-hanging fruit ideas that folks have maybe wanted to try or have tried on ARC. And I think this is now fairly strong evidence 3 months into the contest that we're missing something, likely something pretty big and maybe even as fundamental as deep learning itself. Now, it is going up, right? We got some progress here. It's gone up 14% since we launched in June, which we're really excited about. We're finally seeing some progress. The techniques that folks are that are working are actually quite similar to the techniques that DeepMind's AlphaProof system is using, as well as OpenAI's O1 system. Folks are kind of applying similar techniques to the frontier, and this is actually starting to see some progress, but not quite enough. I also think it's pretty cool that it's special that while AlphaProof and O1 are both closed source, right? We barely even got like blog posts from Google and OpenAI when they launched those things. Hopefully by the end of the year, we'll be able to open source code and frontier approaches on how to actually recreate those systems, and this will be driven by ARC Prize. That's one of the contingents of winning prize money. So while progress is great, I think we still have a long way to go to get up to 85% or even all the way to the 100% mark. Speaking of O1, a few weeks ago, OpenAI released this new model, right? Open. They called it a reasoning model. They said that this is not just another language model. They said that this is a model that represents a system that represents an entirely new potential scaling paradigm for AI towards AGI. When we launched, thousands of people on Twitter were like begging us to test this. Wasn't on our radar, and but there was just so much demand. We buckled down and we did it over the next day or so. And here's the results of what we found. O1 Preview on ARC scores about double what GPT-4o scored, its predecessor. But it's about on par with Claude 3.5 Sonnet. And as you can see, it's very middling in terms of some of the top approaches on the public and the private leaderboard on ARC. They're not pure models, but wrapper code around models. But pretty interesting to kind of see where it's coming in at. Despite its middling score, I do think that O1 is not just another language model. I do think that there is a genuine improvement on generality. In fact, I'd go so far as to say I think it's the biggest generalization improvement we've seen going all the way back to when GPT-2 first got introduced, all the way back in 2019. So it's worth like spending some time to understand what's happening here. O1 fully, I think, exploits this chain of thought technique that language model researchers discovered a few years back, this think step-by-step technique, if you haven't heard of this before. And it exploits this both at pre-training time for the models as well as at inference time, at test time. at training time, O1 is likely generating lots of synthetic training chains of thought, right? Reasoning trains on these domains where they can do a lot of good formal verification. So things like math and physics and code gen. They're also likely doing it in informal domains too, with like reinforcement learning with human feedback on sort of breaking down goals into sub-goals and using that as a reward signal back into the pre-train. And then at test time, O1 is given additional compute time to write search and think over its chain of thought that it generates. Instead of just generating a single chain of thought, it's likely to do search and backtracking in order to try to find better solution paths. These were charts that OpenAI shared in their blog post announcement for O1. And on the left side here, these are both on log scale on the x-axis against compute and the y-axis on accuracy in the first pass. The left side, I think, is kind of what you expect to see on the pre-training side, right? The more examples, the more situations you put into the pre-train, the better the accuracy you're going to get. But I think the new big story, the exciting one with O1, is this test time compute side. OpenAI published this. It's a log linear scale, basically showing the more amount of compute you give to O1 at test time, or colloquially, the more time you give it to think, the more accuracy it can have in the benchmark. Now, I think this fact alone actually makes reporting on things like O1 pretty tricky, and I think this is going to be true for pretty much every single AI model and benchmark going forward in the future too. They're all going to adopt systems like this, where you have choice of how much inference to give at test time. And this means reporting single benchmark scores is actually really deceiving, right? OpenAI made a completely product arbitrary decision on how much compute to give O1 at test time, right? It's a product decision, it's a business decision. Had they set that amount to be higher, you'd see better benchmark scores. Had they set it to be lower, you'd see worse benchmark scores. Now, this log linear accuracy compute chart is not the first time we'd actually seen this chart show up this summer. 2 months ago, just a couple weeks after we launched ARC-Prize, we saw a very similar chart from this guy, Ryan Greenblatt, who's currently the top scorer with 43% on the top of the public leaderboard track. And he found this identical log linear relationship between compute on the y-axis, or on the x-axis, I should say, and accuracy on the y-axis. In his case, his solution was he's using GPT-4o to generate thousands of Python programs for every single task, and then he's verifying. He's actually running the programs to see, does it meet the does it match the input to the output pattern, and if it does, apply that particular Python program on the test. And then he asked the question of, well, how does the accuracy vary on this benchmark if you vary the number of Python programs you generate? And that's what this x-axis is here. It's going all the way down from basically 8 all the way up to 2 to the 21. Ton of examples here. And he found the same log linear relationship. I think fundamentally you see this exponential scaling pattern in Curve anywhere where you're sort of doing brute force or combinatorial search, right? Anywhere you have this order of complexity that's x to the n, I think you're going to see a very, very similar chart show up here. And to beat ARC-AGI this way, you'd need to generate probably over 100 million solution programs per puzzle. Remember, there's 100 of them in the test set. So, could you do that? I guess so. In theory, it's possible. It's computable. We're not in the realm of uncomputability. But would this be AGI? And I think it would not be, not quite. Because back in 2020, and this was before there were any LLMs, before AI at all, the very first version of ARC-Prize was run on Kaggle. And all of the methods back in that era were using basically hard-coded domain-specific languages with brute force combinatorial search applied over that DSL. And at the end of the contest, one of the moderators looked at an ensemble of all the solutions that got submission through the entire contest and found that about half of all the ARC tasks today in the private set could be beat just with brute force search, with no AI, no LLMs, nothing special. Half the benchmark could be beaten that way. I think practicality alone often just rules out this O of x to the n, this combinatorial search complexity problem. And more importantly than that, I think than practicality is that actually efficiency matters a lot to the definition of intelligence. I think it's a hallmark of intelligence. In fact, I think it may have even been the sort of single intelligence, the single gradient that evolution followed in order to increase intelligence, where you sort of want to have increasing intelligence or increasing efficiency in order to decrease risk, better navigate your environment, more quickly find food, more quickly navigate away from danger. I also think you can consider when you're taking your own ARC tasks, right? If you introspect how you take these, often you're looking at the puzzles and you're trying to see a couple program solutions in your head, and then you deterministically check them, right? What you're not doing is generating thousands or even millions of programs and then checking them. You're able to use your perception network to shrink the search base quite a bit. All right, now before I hand over here to Francois to get into how to beat ARC, I think I'll summarize O1 like this. I think O1 does represent a fundamental paradigm shift. I think OpenAI was accurate when they said this. I think it represents a paradigm shift from a mode of language model scaling and training where we're just memorizing answers to a new regime where we are now memorizing reasoning chains. But importantly, you're still memorizing. We're still working within this broader paradigm that hasn't been broken yet, which is one where you're trying to increase accuracy on performance based on these systems by just giving them more and more situations and examples. So if LLMs can't beat ARC, if O1 can't beat ARC, and all of the existing frontier approaches to AI, now 3 months into ARC Prize, can't beat ARC, what could? And to help illuminate the path forward towards AGI, I'm going to hand over here to François Chollet. There you go, François.
Thank you, Mike. All right, can you hear me all right? Yeah, looks like it's working. Cool. So yeah, let's talk about how we can beat ARC. And let's get started with, let's take a look at what's special about ARC, because that's the million-dollar question, like, why has it not been beaten yet? So like Mike was saying, ARC is not difficult. The tasks are not complex for humans. It's actually very easy for humans. It doesn't require any special knowledge, any special training, just core knowledge, which any 5-year-old must have mastered already. There's just one thing. It's designed to be resistant to memorization. So each task is unique. You have to approach each task from scratch and figure it out on the fly. And in the past few years, there's been a lot of talk about how LLMs can perform in-context learning to adapt to new problems on the fly. And if you look more closely, what seems to actually happen is that LLMs are fetching memorized programs that map to the current prompt. If they don't have a memorized program ready, if they're faced with something that's slightly unfamiliar, even if it's very simple, they're going to fail. And that's true even if the novelty that they're facing comes in the form of a small variation on the problem for which they did memorize a solution. And there are many, many examples of this across different benchmarks, including ARC-AGI, of course. But we can look at even simpler problems. So here's one example. LLMs can solve a Caesar cipher, which is this very basic form of encryption where you're just moving the index of a letter by a fixed position. But as it turns out, they can only do this for fixed values of the key size, like 3 or 5. If you show the same problem with different key size, the LLM is going to fail. So basically, they don't have any understanding of what this Caesar cipher is or how to solve it. They've just memorized solution programs for specific key values, key size values. Another simple example is Alice in Wonderland type problems, which is the question you can see here on the right. It's questions of the form, Alice has n brothers and also m sisters. So how many sisters does Alice's brother have? So as a human, if you're seeing this question for the first time, it doesn't take you too long to figure out that, yeah, the answer has got to be like m plus 1. It's m, the number of sisters, plus Alice herself. And as it turns out, LLMs can answer this question correctly, but only for specific values of m and n. If you're showing them unusual values, they will fail. So again, very, very interesting. They're just memorizing point-wise solutions, basically. So my hypothesis, and it's an hypothesis that's been formulating a long time ago, and it just keeps getting confirmed, is that LLM performance depends purely on task familiarity. So you can make an LLM do anything you want, but only if you give it the opportunity to memorize the solution. Right? It cannot adapt to the slightest amount of novelty, even if the problem is super simple, like in the case of ARC-AGI, where the tasks are easy for humans. And that's not just LLMs, by the way. That's broadly a limitation of the curve-fitting paradigm of deep learning in general. So the way I think about an LLM is as a database of skilled programs. So a skilled program is just this function mapping a set of situations to the appropriate response. And an LLM is just that, but covering many, many different skilled programs in many, many different situations. So when you're training your LLM, it's trained to predict what's next, given an input token sequence. So it's basically trained to produce functions that go from a pattern of input tokens to pattern of output tokens. And if the LLM had infinite memory capacity, then it could learn these functions via some kind of lookup table, just literally store where the input was and where the corresponding output should be. But that's not the case, of course. LLMs have not infinite memory capacity. They only have so many parameters. So what happens is that they're forced to compress the skill program space that they're encoding. And they do so by representing new programs that they need in terms of bits and pieces of old programs that they've already memorized. And by doing this compression, LLMs learn to generalize a little bit outside of what they've seen before. This is what makes LLMs useful. If they weren't doing that, they would be purely lookup tables. And anytime you're prompting an LLM, what you're doing is basically that your prompt is like a database query that's retrieving one or more such skill programs and applying them to your input. And that actually perfectly explains scaling laws. If you're measuring model performance based on the score that you get on exam-style benchmarks, where the skill programs that you need can be memorized in advance, then performance is just going to increase as a function of the number of tasks, the number of skill programs that you've memorized, and the number of situations that you've memorized. And that is to say, it's just going to increase log linearly as a function of the amount of training data and the parameters that you have to store it. My take, personally, is that intelligence cannot be reduced to just memorizing every possible task, every possible situation that you might ever encounter. So here are some key concepts that you should be taking into account if you really want to understand the nature of intelligence, if you want to define it and measure it. The first thing to keep in mind is the distinction between static skills and fluid intelligence. So between having access to a collection of static programs to solve known problems versus being able to create a new skill program on the fly to face something that you've never seen before. And it's not one or the other. There's a spectrum between the two, but intelligence is, of course, on the side of fluidity, and LLMs are on the side of the static database of static skill programs. And the next concept is operational area. If you're looking at the skill programs that you did acquire already, not all skill programs are equal. Some of them are only going to be able to make sense of situations that are very close to what the system has seen before. Some of them are going to be much more abstract. They're going to be able to cover a much broader range of future operational space. And of course, higher intelligence is on the right side of that spectrum. And the last concept is information efficiency, right? How much data, how much information was required to synthesize, to learn a new skill program. And of course, there's more intelligence on the side of information efficiency. So the big takeaway I want you to remember is that skill is not intelligence. Skill and intelligence are entirely separate concepts. And you can always display skill at any number of tasks and not show any intelligence. It's always possible. All you need is a big lookup table. If you just prepare for your exam by blindly memorizing every possible answer to every possible question you might be getting, you're going to get perfect grade, but you don't actually need any understanding whatsoever of the source material to achieve this. You just need a big lookup table. And it's really like the difference between having a road network versus having a road building company. If what you have is a road network, then you can move from A to B from a fixed set of A's and B's, and you cannot really do anything else. If you have a road building company, you can start connecting new points to each other, new cities to each other as your needs evolve. And intelligence is more like the road building company. Really, skill is the outcome, the output of a process. The process is intelligence. So do not confuse the process and its output. Don't confuse the road and the process that created the road. And personally, I want to make more intelligent machines, like machines that can actually apprehend brand new problems and make sense of them autonomously without having memorized the solution in advance, and do so efficiently. And one really important thing to understand about model building ability, the ability to turn information into models that will generalize, is that it's really a spectrum. It's a spectrum of model abstraction that goes from pure memorization of pointwise factoids to organized knowledge that will generalize somewhat, to models that will be abstract and will be able to generalize strongly, to meta models, to the ability to produce new models, to adapt to new problems. And this is where intelligence lies, to finally the ability to do so efficiently. And the degree 0 is when you are purely memorizing pointwise factoids. There's no abstraction involved. You're not going to generalize at all past the set of situations that you've seen before. So here are factoids. We have 3 factoids. I picture them as functions. And these are functions that take no arguments. So that's how you know that they're not abstract. But once you start having lots of factoids, you can try to organize them into more abstract functions that encode knowledge. So here, this function, you can tell it's somewhat abstract because it takes an argument, x. So it is abstract for x. And curve fitting, so deep learning in general, is really good at this kind of knowledge organization. It's going to be basically embedding pointwise factoids on a curve, and then it gives you the ability to interpolate on the curve between your factoids. But the problem with this kind of abstraction, this kind of generalization via interpolation between pointwise factoids, is that it looks like abstraction, but it's very weak abstraction. It might return something incorrect. It might hallucinate. It might not work well if you're far outside the trained data distribution. And the next degree beyond that is to turn your knowledge into abstract models. So a model does not encode factoids anymore. It does not encode a curve that interpolates between factoids anymore. Instead, it encodes a concise way of processing an input to obtain an answer. This kind of model will be able to generalize strongly. So it will always return the exactly right answer, not an approximate guess. And it will be able to operate over any input in a broad range. So unlike LLMs, for instance, if you ask LLMs to add numbers, they might be more or less right depending on the input numbers. And the stage beyond that is the ability to generate abstraction autonomously, to synthesize such new abstract models on the fly. And this is how you're going to be able to handle novel problems like ARC-AGI tasks, things you've never seen before. And this is what intelligence is, as opposed to just knowledge and crystallized skills. And the last stage is to be able to do so in a way that is maximally information efficient. So that means that you should be able to master new tasks using very little experience, very little information about the task. And not only are you going to be able to display very high skill at the task, meaning that the model that you've created is abstract and can generalize strongly, but you only have to look at very few examples to achieve that. And this is how I would define AGI. And right now, we're still pretty far from it. So if you want to place LLMs on this spectrum of model abstraction, they're basically at the organized knowledge stage. They're not yet quite at the generalizable model stage, because if they were, they could actually reliably solve a Caesar cipher for arbitrary key sizes, or answer Alice in Wonderland type questions, or add numbers. So they're not quite there yet. But they are clearly more than just pointwise factoids. An LLM is not a lookup table, because the knowledge it contains is highly compressed and structured in such a way that it can, in fact, generalize to lots of things the model has not seen before. It's weak abstraction, but it is still some degree of abstraction. And if we solve all the problems that are plaguing LLMs today, like hallucinations, the patchy generalization, the high sensitivity to input prompts and so on, you get to the model stage, which would be tremendously useful, for instance. This would be many potential billion-dollar businesses. But to get to autonomous model generalization, that's actually a big step. You cannot get there by purely scaling current methods. It's a paradigm shift. You're going from program fetching to actual programming. And to get there, you have to change direction. And beyond that, getting to AGI is still pretty far off. So concretely, how do we start making some steps in the right direction? How do we make machines that can autonomously produce their own models on the fly? And the answer is abstraction. Abstraction is really the engine of generalization. It's the engine of modeling. And abstraction is pretty much the process of turning observations into reusable building blocks that you can use in new models. And you do so by noticing analogies between different observations, erasing away the stuff that doesn't matter, and merging your observations into prototypes, into reusable programs, something that's going to be a building block in your next model. And importantly, there's more than one way to make analogies between two things. I count exactly two ways. There are two key categories of analogies from which arise two categories of abstraction. There's value-centric abstraction and program-centric abstraction. And they're pretty similar to each other. They mirror each other. So both are about comparing things and merging them together to create a prototype or a program. And you do so by erasing the stuff that doesn't matter. The key difference between the two is that one operates over a continuous domain and the other operates over a discrete domain. So value-centric abstraction is about comparing things via a continuous distance function. So you're basically looking at two things and you're trying to tell how similar they are in terms of degree of similarity. And this is the kind of abstraction that powers human pattern recognition, intuition, perception. And meanwhile, program-centric abstraction is about looking at things that are effectively programs. So they are graphs. And you're looking for exact subgraph isomorphisms. You are looking for substructures that are exactly contained in the different instances that you have. And this is the kind of abstraction that backs human reasoning. It's also what software engineers do. So if you hear a software engineer talk about making two functions abstract by refactoring them, they're talking about exactly this. They're talking about extracting subgraph isomorphisms. So both forms of abstraction are powered by analogy making, but it's two different kinds of analogy making. Value analogy is grounded in geometry, so you're using this continuous distance function, and program analogy is grounded in topology. You are comparing substructures and doing comparison via exact matching rather than degree of similarity. And I really believe that all cognition, all intelligence emerges from a combination of these two forms of abstraction. And one way to remember them is the left brain versus right brain kind of metaphor, which is, of course, purely a metaphor. It's not actually how lateralization of cognitive function works. So one half for perception, intuition, pattern recognition, and one half for slow reasoning, mathematics, planning. And it also mirrors the system 1 versus system 2 analogy from Kahneman. And transformers are a great type 1 abstraction machine. They can do everything that type 1 is good at, like perception, pattern recognition, and so on. So in that sense, I do believe transformers, deep learning more broadly, represents a major breakthrough towards AGI. But they're not yet a good fit for type 2 abstraction. And this is where all the limitations that you know about LLMs, transformers, and deep learning in general come from. This is why you cannot add two numbers reliably with a transformer, even if you train it on all the data on the internet. So how do we go forward from here? How do we get to type 2? And the answer is that you have to leverage discrete program search as opposed to purely manipulating these continuous interpolative embedding spaces that you learn via gradient and descent. And that is an entirely separate branch of computer science compared to deep learning, compared to ML. And we have to merge it with deep learning in order to get to AGI. So what's discrete program search? It's combinatorial search over graphs of operators taken from a domain-specific language, a DSL. So to better understand it, you can draw an analogy between machine learning on one side and program search on the other side. In machine learning, your model is a differentiable parametric function, so it's a curve. And in program synthesis, your model is a graph of operators taken from a fixed DSL. In ML, your learning engine, the way you create new models, is gradient descent. And in program synthesis, you're going to be doing combinatorial search. In ML, your feedback signal is this continuous differentiable loss function. And in program synthesis, you're just going to do an exact correctness check. So you create a program, then you run it to see if it checks out. And the key challenge in machine learning is really obtaining a dense sampling of the problem space. You basically need tons of data to fit a model. Program synthesis is the exact opposite. You can actually fit models via program synthesis using just a few data points. It is extremely data efficient. But the problem is that the size of the space of programs that you have to search over grows exponentially with problem complexity or DSL size. So the key challenge is combinatorial explosion. And when I first launched the ARC competition, like the original one in 2020, I predicted that the winning entries would all use program synthesis. And as a matter of fact, they did. The winner scored 19% back then using just brute force program search. And today, so this technique has been refined, and the highest score you get with this technique today is about 36% on the private leaderboard. However, we know that some version of this technique, if you really scale it up, can do up to about 50%. And that was true already back in 2020. If you just scale up brute force program search, that's what you get. And by the way, this has not been beaten yet by any known technique. And meanwhile, if you look at LLM-based approaches, via direct prompting, you can get up to 21% with O1 or Claude 3.5 Sonnet. And if you start doing LLM-driven discrete program search, you get a much higher score. You get potentially between 40 to 50% each, which would be state of the art. So discrete program search has proven to be this really powerful tool to approach this kind of reasoning problem like ARC, and LLMs are also starting to show strong results, which is very new, by the way. LLMs only really started working this year. Previously, like GPT-3, for instance, scored effectively 0 on ARC-AGI. So I said earlier, all intelligence is a combination of two forms of abstraction, type 1 and type 2. I really don't think that you can go very far with just one of them, with like just deep learning or just discrete program search. You need to combine them to unlock their true potential. And I believe that's what human intelligence is really good at. That's what makes human intelligence special, is that we combine perception and intuition together with explicit step-by-step reasoning. We combine both forms of abstraction. We very rarely do anything that is just pattern recognition or just reasoning. We're always mixing them. This is what you see, for instance, in chess. When you're playing chess, you're using type 2 when you're calculating, when you're unfolding some potential moves step by step. But you're not going to be doing this for every possible move because there are way too many. You're only going to be doing this for a couple different options. And the way you narrow down these options is via intuition, is via pattern recognition. You just look at the board and see where the interesting moves are, and you're building that through experience. And that's very much type 1. That's canonical type 1. So you're using type 1 intuition to make type 2 calculation tractable. So how would it work concretely in an AI system? Well, the key system 2 technique is discrete search over a space of programs, and the blocker that you run into is combinatorial explosion. And meanwhile, the key system 1 technique is curve fitting and interpolations. You embed lots of data on an interpolated manifold, which enables you to do fast but approximate judgment calls about some target space. And the big idea is going to be to leverage those fast but approximate judgment calls to fight combinatorial explosion. So use these judgment calls as a form of intuition about the structure of the program space that you're trying to search over to make search tractable. A simple analogy, if you want to understand what we are doing here, is drawing a map. What are you doing when you're drawing a map? You're taking a bunch of discrete objects that have discrete relationships that would normally require combinatorial search, like path finding, for instance, is a combinatorial problem. But then you're going to embedding these objects into a geometric manifold where you can use a continuous distance function, like L2, for instance, to compare them and to make fast but approximate judgment calls about things like directions, distances, path finding, and so on. And this enables you to keep combinatorial explosion in check. So two exciting areas to combine the strength of deep learning with the strength of program synthesis would be, first, to use deep learning components side by side with System 2 type components. So for instance, you can use deep learning as a perception layer to parse a situation into discrete building blocks that can then be fed into a program search engine. You can also start adding symbolic add-ons to your deep learning models, so what's known nowadays as tool use. And the second direction is to use deep learning models to inform discrete search to improve its efficiency. So use deep learning as a kind of driver, as a kind of guide for program synthesis. It's going to give you, for instance, intuitive program sketches to guide your search. It's going to reduce the space of possible branching decisions that you have to look at. And in the context of ARC-AGI, there are two ways this could actually take shape. So you can listen closely here because I'm going to spell out to you basically how to solve ARC-AGI and win the $1 million. There are two big directions that you can go. So the first one is that you can use deep learning to sort of draw a map of state space, of grid space. And in the limit, this solves program synthesis. And here's how. Let's say that you've created a manifold where points represent grids, like arc grids. And the distance between 2 points is a guess about the number of symbolic transformations that you're applying to one grid to get to the next grid. In that case, the way you solve the problem is that you embed the input grid on your curve, then you embed the output grid on your curve, and then you just draw a line on the manifold, right, that interpolates between the two. And this line interpolates a number of intermediate grids, intermediate points, which decode back to grids. And this grid sequence is a guess as to what is the exact sequence of DSL transformations that go from input grid to output grid. So you're turning effectively program synthesis into an interpolation problem, into this interpolative space in which you can make a very, very fast judgment calls, again, that translate back into guesses about the structure of program space. And the other direction you can go is program embedding. So you're drawing a map of program space this time. And this map will make it possible to make the discrete search process more efficient. And so for instance, you can use some kind of LLM or deep learning model to generate candidate programs, and then you check them with an external verifier. This is what Ryan Greenblatt is doing, for instance. Instead of generating exact programs, you can generate more like sketches that then you can give to a discrete search process to refine them, and so on and so on. There are many different ideas you can try. And right now, we've only just started scratching the surface in terms of exploring all these different ideas. And I strongly believe that within just a few years, within probably a couple years, we're going to crack ARC-AGI. And that's not going to mean we're going to have AGI right away, but it's going to be a big milestone towards AGI. And I strongly believe that the solution is going to be built on top of these ideas. And maybe it's going to be built by one of you. So now I'll turn it back over to Mike, and Mike will tell you how you can get involved with ARC Prize.
All right, wrap up slide here, and we'll do all the Q&A. So why are we on this tour? Why did we come to your all school? Well, we are trying to find the person who's going to beat ARC. Even though we've made a lot of progress on state-of-the-art this year, this summer, there's really not been that much conceptual progress. We still only have a handful of teams that are scoring above 30%. I think there's only 2 teams that are scoring at or above 40%. The grand prize is 85%, so we got a long way to go. And I think the solution is going to come from an outsider. I think it's unlikely to come from someone at one of the massive labs training billion parameter, trillion parameter models. I think it's going to come from somebody outside merging sort of unique ideas together on how to crack this thing. In fact, my own personal belief is that the solution to ARC is going to be relatively small. I bet it's a 7B model and smaller, and 10,000 lines of code or smaller. I think these are very tractable within the sort of realm of individuals and small teams and small labs to reach. And hopefully it's one of you in this room is going to be the one who did. So ARC Prize 2024. I just realized this says 2004. We should update that. ARC Prize 2024 wraps up on November 10th. So not too far away, but importantly, we don't expect there to be a grand prize winner this year. We're so far away from the grand prize score. So what we do have is we've got some progress prizes. So we're going to pay out cash this year no matter what. We've got $50K going to the teams that get the top scores this year on the Kaggle contest. And we also have a paper track, so we're going to be giving $75K away to the couple top teams that submit papers as part of the contest that advance the conceptual progress the furthest, as scored on a rubric that François and I are going to grade at the end of the contest. We're going to be announcing the winners of all this stuff early December, and we're also going to be at NeurIPS this year as well. We're going to be part of the System 2 Reasoning Workshop, where we're going to be using that moment to go over all the winners, and importantly, show all the new code, show all the new open source approaches, walk through what are these teams doing that are scoring, winning these top scores, and use the downtime this winter to hopefully re-baseline the community of people working towards ARC on what are the frontier approaches, what's working, right? What's getting to that 50% with AI and LMs and all that. In order to go into next year's contest, probably early in the year, with everyone re-baselined at that new high level, that new high watermark, which hopefully will just stair-step our way all the way up to the 85% and get this thing beaten in the next couple years or so. We also have a new public leaderboard. So all the prize money is attached to the Kaggle private leaderboard, the state-of-the-art 100 puzzles. We also have a new public leaderboard. And this is a great way to get started into ARC. It's a very accessible entry point. Unlike Kaggle, which doesn't allow you to use sort of APIs for security reasons, the public leaderboard does. You get to use commercial API models like O1 or GPT-4o or Claude or anything like that. And while there's no official prize money for the public track, it's more of an academic track, there is a reimbursement fund that we set up for it. So if you're working as part of a lab and you want to verify high score on that, we'll reimburse. We got $100,000, $150,000 verification fund set up to work with teams to verify high scores on that side of things. So you can get started there. ARCprize.org is the website to go to. It's got all the details to join the contest. There's also a lot of really good technical resources on. Greg wrote this awesome technical guide on summarizing all this ARC history, the data set, the distinction between all the data sets. All the past approaches are sort of aggregated in one spot too. It's really, really, if you're going to do it, just start there. We've also got links to the Discord. There's an email list I'd recommend signing up for. And my personal favorite is the ARC Prize Twitter account, which if you don't do anything else and you're interested in ARC Prize, you should follow this link or follow this account. We are sharing relevant frontier research papers that come out in the realm of deep learning and program synthesis and discrete program search that we think are relevant and people should try to go explore. So if you're hunting, if you want to work on ARC but you're not sure how to get started, or you're looking for a new idea, we're tweeting them a couple times a week. So that's worth following. And then my favorite thing the Twitter account does is it also tweets out every single percentage point towards the grand prize here. So if you're like me and you kind of want to you're sick of all the AGI scaling hype, and you just want one thing to pay attention to be like, hey, do we have AGI? Are we there yet? How close are we? You can follow the ARC Prize account and get your dose of that. All right, now we're going to open up to Q&A. Are we going to use the Dory?
François, I'll have you come over here. All right, so just very quick logistical first. We're going to do about 10 to 15 minutes of questions. Then we'll take a break, and everybody can go about their day. But we will be hanging out in this room if anybody wants to talk even more privately. I'm sorry? How long are we here? We are here. We have the room. We'll be here until 3 p.m. So, but we'll do just questions for about 15 minutes here. So Mike and François, first question from the crowd. And again, if you want to ask questions, please go to the QR code and submit it here. I'm looking at them live. How are you protecting yourself from Goodhart's Law? And to remind everybody what Goodhart's Law is there's a quote: when a measure becomes a target, it ceases to be a good measure anymore. So how do you think about that?
Sure. So, yeah. So the entire benchmark is designed to protect against this. this is in the measure of intelligence paper. I refer to this as the shortcut rule. The fact that if you create a benchmark, you create a new measure, people are going to find the shortest path to get there. And it might be that this path is completely orthogonal to what you set out to achieve with the benchmark. And the way ARC is designed to protect against that is first that what we evaluate on is an entirely private test set. No one has access to it, so you cannot train directly on it or handcraft a model that will perform well on this evaluation set, but not on anything else. And the other thing is that every task is intended to be unique. It's not like there is a distribution of ARC tasks that you could just fit to, and then you can solve any ARC task. You just do not know what task you're going to get next. It could be anything. And so in order to perform well, you actually need to create a model that can approach anything, and which is precisely how we define general intelligence.
One add thought there is a form of that question that I think we've gotten asked a lot is, does a solution arc actually mean you have AGI, right? Is it actually a good target in that direction? Or you were sort of overfitting on this weird puzzle, right? It's like, oh, we beat ARC and whatever, doesn't matter. You know, the field is rich of benchmarks, toy benchmarks that have gone down that path. And I think one of the things that makes ARC really special is, and maybe the strongest statement you can make about what a solution arc is that it's a canary for AGI, because ARC will like necessarily get beaten once we have AGI. So I think you can have a pretty strong statement that we do not have AGI if ARC is not beaten yet. Now, will it be the full version of AGI that I think we sort of envision with, you know, human level efficiency that can operate over like multimodal domains? I don't think so. I think it's going to need to get scaled up and applied to a lot of different domains. But I do think it will be a necessary condition, but not a sufficient one for AGI.
Wonderful. Next question here. How can we effectively measure a vision language model's ability to understand ARC? Or to put another way, is ARC just a visual exercise, and having a vision model will help us with this?
I can take this one. So, not at all. ARC is not a visual benchmark. This is a widespread misconception that because we organize the tasks as grids, it's a visual benchmark. Actually, it's not. It's purely about symbolic relationships. What we found is that if you tokenize the tasks, so if you just translate them into sequences of tokens, it is very easy to train a transformer to solve one specific type of task. So transformers, for instance, which are pure sequence models, they have no vision components, they have no trouble solving our tasks in terms of being able to tokenize and represent solution programs. The only reason why transformers have not solved ARC yet is really because the tasks are unfamiliar. So the obstacle is the unfamiliarity, not the visual aspect. In fact, what we found is that, well, vision language models have been introduced, you know, starting a couple of years ago, and there are many strong ones that are open source today. There are also some that are just available as APIs, and none of these models so far has performed better than just plain transformers. The state of the art today, using LLMs, is using a pure sequence model. It's not using any sort of vision component. So there's pretty strong evidence that no vision doesn't actually matter. The reason why we made it 2D as opposed to just 1D is just to better interface with human test takers, but that's the only reason.
There's one other like sort of analogy you can draw here, I think, which is you know, the sort of spatial information. We didn't show this on the slide, but the actual data format of the ARC puzzles, it's rendered visually for when we like show it to people in humans, so you can actually get it. The actual data format is like a JSON 2D matrix with just like arrays of numbers and integers going from 0 to 9. All the colors are arbitrary. You could choose any color palette you wanted. The color doesn't matter at all. So effectively, it's code, right? Now, code does have some spatial like semantic information, especially a language like Python, right? Like, you know, how far, you know, your code is indented actually has semantic meaning in the language. So to the degree that there's like spatial like representation and layout matters, like in code is, you know, I think that's necessary for ARC. But a visual model isn't necessary. I think it can help, but I don't think it's necessary.
Beautiful. Next question is around agents here. How are agentic AI systems faring for this problem? Or is that considered, quote, cheating, end quote? That is, could we have type 1 and type 2 reasoning via multimodal agents?
I mean, you cannot really cheat on ARC-AGI. If you can make a system that solves it, it basically doesn't matter. The worst case scenario is that you've just uncovered some flaw of the benchmark, and that's your. But that's not cheating. It's actually well within the rules, right? And I'm not sure what is being meant here by agentic. Different people mean very different things by that. But if it just means a model that is itself made of multiple sub-LLMs like calling each other, that's entirely valid. That's entirely within the rules. Right?
And probably not too dissimilar to what you see with like O1. I know you wouldn't typically call O1 an agentic model, but in its like search and background tracking, it's probably doing. I would speculate that O1 in its like inference time compute to generate chain of thought is doing parallel inference, and I think that's one of the key concepts with agents is you have like parallel inference and systems running.
Wonderful. Next question here. I was quickly able to solve the ARC problem on the screen, but I'm not convinced that it's actually easy for an arbitrary AI. What do you think of ARC tasks being, quote, in domain, end quote, for humans' inductive bias?
That is explicitly the case. ARC tasks are built on top of human core knowledge priors, which is intended to be the set of knowledge priors that all humans possess and acquire very early in life. And this is deliberate choice because we've created ARC to be able to compare human cognition and AI, to be able to have a shared scale of intelligence for humans and for machines. So yes, ARC is very human-centric, and that's deliberate.
There's some fun, what's that puzzle we saw? There's some fun puzzles where we found that like, after we started launching this thing, that are actually have the opposite property, right? Like we want the tasks to be easy for humans, hard for AI. But we actually found that there were some sets of tasks that were actually hard for AI, or hard for humans, easy for AI. Kind of the opposite. They tended to take the form of the ones that like stressed the visual perception system. They had a lot of noise. They usually were like the larger state space on the grid. And that's actually one of the areas I think we know ARC is not perfect as a benchmark, and we want to improve on it in the future. Is minimizing the degree of these benchmark tasks that we actually have some evidence now are actually difficult for humans and easier for brute force methods.
Beautiful. All right, last question, and then we'll take a break and we'll stick around with everybody from here. So when or if we solve ARC, what types of challenge comes next? Will it be similar to ARC but scaled up, or will it be fundamentally different?
So I think once we've solved ARC, we've got a pretty strong candidate answer for the question, what does it take to create machines that can adapt to tasks that they've never seen before, to things that they've not been prepared for? And after that, there are many next problems, like open-endedness, goal setting, embodiment. My take is once we have a strong ARC solver, the next step is going to be to move to game environments, to very open-ended game environments with embodied agents operating in them. And the next benchmark is going to be along these lines.
I'll take a different track on the question, just to give another flavor. One of the things that I think I will do very first once we get a solution to ARC open sourced is take it back to my Zapier co-founder, Brian Helmig, is the CTO, and use it to immediately start figuring out how do we increase the reliability and the consistency of all of our AI bots in Zapier. That's like the number one piece of feedback we get from our customers is they hesitate to deploy AI for their businesses because they just don't trust enough. It fails in non-human ways, it's inconsistent, it's unreliable, and I think that is one particular thing that a solution to ARC can help solve that LMs have not been able to yet.
Mm-hmm. I mean, yeah, if you have a solution for ARC, what you've effectively solved is automated programming. You've created a system that can take an input, the output that you want, and it can automatically generate a program to go from input to output. And there are pretty good reasons to believe that this would not be restricted to just grids of 2D symbols, that it would work across arbitrary mediums. And of course, if you solve programming, if you solve automated programming, you're solving many different billion-dollar problems all at once.
Beautiful. Well, thank you very much for coming today. That's it for the presentation. We'll be hanging out here for any additional questions. Thank you all.
Thank you. Thank you.